So this is 10 per second, and if all we know about this single neuron is this firing profile, the natural thing to think is all there is firing rate, and that's all. Now, firing rate of single units have been studied now for, I don't know, 70 years or so. And there are a lot of publications and works on this. And indeed, we do learn some interesting things. For instance, I'll give you two examples. Georgopoulos on the primary motor cortex. A monkey is trying to press a central button. Then one of 8 targets around it leads, and it moves to this target and press it. So here is the activity of this neuron during this task. If it moves to the left, you get this profile of activity. If it moves to the right, you get this profile of activity. And you can see that there is tuning for direction. It's most active in this direction, less in this, and it's inhibited in this direction. Georgopoulos measured single unit activities in this way for hundreds of neurons in the primary motor cortex. And if he thinks of this activity as the rate of firing here, as the size of a vector pushing the arm in this direction, and you have 100 or 200 neurons like this, so you get for each direction 200 vectors. If you sum them vectorial, it will be in this direction. And if the same neurons you sum their vectorial activity in this direction, it would be here, not exactly to the right, but close enough. So the idea is that firing rate here drives the arm in a certain direction, and that's all that there is in there. But Georgopoulos himself have done more complicated things. So this is taken from the book 101 Ways to Make Your Subject Crazy. So that's what the monkey has to do. He presses a button, and then after a while, target 1 is turned on. So target 1 is down there. After another half a second, target 2 is turned on. And then target 3, target 4, and target 5. And then one of the targets, in this case 2, change the color to blue here. And the monkey has to press the target that was one after this one. So after target 2 was target 3, or this target was this target, and the monkey moves to this direction. Now we recorded single units in the primary motor cortex of these monkeys and try to see to what feature of what's going on here the monkey, the unit, the neuron, raises its firing rate. And as you see here, you cannot read this, most of the neurons fired to the serial order of the target. So a neuron fire when the target is number 2, no matter whether it's this target or this target or this target or this target, just the serial order. Most units do this. Only few units are responsive to the direction of the movement. So the same neurons that seem to be directed the arm is doing something completely different in this complicated task. In my mind, this means that firing rate is not the entire story. Another example, visual cortex, V1. So everybody knows, this is from a textbook, that a neuron is sensitive to direction of line or edge. In this direction, it fires the higher rate, lower in this, and none in this direction. And it does firing more when the target is moving, either in this direction or in this direction. So in V1, neurons are sensitive to the direction of a line or edge and their movement. This. So I want to show you an example that casts doubt on this idea that firing rate of neurons in V1 is all to image recognition. So here is something that you see these garbled things, and it's not clear if there is any object here. But if I just move a little the masking, you immediately see the object. So what's going on in this direction? Even if you fixated on the red cross and I move the rest, you would see this object. Now, if you are fixated on the red cross, then the neurons that are responding to the object will fire less than the rest of the neurons that are responding to pieces of lines in the correct direction that are moving. Yet, the neurons that fire in lower rate generate the perception of the object. So there must be something beyond just the firing rate of neurons that let us connect these pieces of lines into an object. That's for masking the view. So again, what happened? The figure was stationary, the mask moved, but it would be the same even if we reversed it. The mask was stationary and the figure moved. Neurons responding to parts in the figure were firing at lower rate compared to those responding to the mask. Yet the neurons that responding at lower rate generated a figure. But there were many, many other neurons responding at low rate. They were not affecting the perception of this figure. The conclusion is that there must be something beyond just firing rate. It can't be just firing rate. Let's see, look. Okay. So the conclusion that there must be something beyond just firing rate. Okay. Now, how can we test if there's something beyond firing rates? Here is a page with some text. It takes measurements through several points in parallel to reveal an internal structure in the code. What do I mean? I mean, suppose some alien came to Earth, and aliens, as you know, have one pixel vision only. And now this alien is looking on this text. If you look at it on it with one pixel only, you usually would see a black dot, which you don't see anything here. Sometimes you would see a white dot, like in this case here. And if you don't know anything else, you just try different position, and there is either one black or one white dot, and you think that all there is in this text is density of white dots, like firing rate. Now, suppose you measure simultaneously to two pixels. You would see many cases like this where both of them are white. There are less cases than only one pixel is white, but the number of cases that you see something like this is much higher than expected if the white dots were scattered at random on this page. And this becomes even more obvious if you do it, oops. If you do it through 3 pixels. So like here, all three are white, or like here, all three are white. The number of cases with 3 pixels white is much lower, but it's much, much higher than what you would expect by chance if the white thing was dots scattered at random on this picture. So how can we test if there is something beyond firing rate? So we saw that with 1 pixel, we cannot know this, but with 2 or 3, we can see that can know that there is some structure. Here is now back to neurons. These are cross correlations between 2 neurons recorded through nearby electrodes. You can see that there's usually, so let me explain, this is delay. 0 is the time that neuron 1 fired, and we count how many cases also neuron 2 fired, that this delay, this delay, this delay. And you can see that at 1 or 2 beams where the coincidence of firing at 0 and firing at here something like 200 milliseconds is much higher. This is another example with shorter delay. This is another example with delay of almost 400 milliseconds. So when we record 2 single units and do cross correlation, it's like looking in 2 pixels on this picture. We find such sharp peaks, and it means that there's something beyond firing rate. But we don't know what it is beyond the firing rate. You can do it with 3 neurons. So this is a cross correlation, triple correlation between 3 neurons. Neuron 2 is considered time 0. Here is the delay to unit 12, and here is the delay to unit 13. You can shuffle the trials and you subtract the shuffled from the real counts, and you get this picture. If we look around this region in 3D, you see something like this. Okay, so this is the counts minus the shuffle, and you see this peak is standing way above the background. If you look what's in it, you can see that counts in this bin happen when unit 12 fired, and 11 milliseconds later, unit 2 fired, and something like 400 milliseconds later, unit 13 fired. So there's a combination of 3 firing rates that occur much more than expected by chance. Here is another example of this sort. You may think that there are stimuli, and this unit is time locked to the stimuli, and this is also time locked to the stimuli, and this is also time locked to the stimuli. So you get this sequence. So down here is all the stimuli. The down pointing arrow is visual stimuli. You see that this triplet occurred sometimes after a visual stimulus was presented, but it's not time locked to the presentation time. So the internal time locking here is very accurate. Time locking to the stimulus is very loose. Now, how can we get what's going on in the cortex? You could say that if we recorded all 10 to the 10 neurons in the cortex, we would know what's going on. I think we would be confused completely and not understand what's going on. So I'm trying to argue what should you do to understand what's going on. So the first fact is that cortico-cortical connections are patchy. This is an example from the work of Rafi Malach. In B1 of monkey, he injected here an antrogate tracer, waited from some time, so the tracer had time to propagate about 10 millimeters, and look where are the targets. And you see, except the neighborhood, there are many, many patches that are recorded. So it's a point is not connected to everywhere loosely, but densely to some patches around it. So here he waited only something like 10 days. So you see some of the patches. If you wait more, you will see more patches. So in the brain of us, in our brain, how many patches like this would be connected to each patch? So here's an argument. In the mouse, this can be really measured. And Almut Schutz measured it and found that usually each point is connected to 5 cortical patches. Now, Valentino Breitenberg speculated that the number of patches would grow like the square root of the number of neurons in the cortex. Now, that would mean if in the mouse there are 5, in human beings there are 150. That is, each point in the cortex is connected to 150 patches in the cortex. That maybe explain why we are smarter than a mouse. Now, in each patch of human cortex is about 1 millimeter square. Under it, there would be about 40,000 pyramidal cells that project to other places. So that means that connection between 2 patches is something like 200 by 260 neurons. So we can hope that if we can record from these 260 neurons, or a large number of them, we can understand how the patches talk to each other. Now, with 260 neurons, you have millions and millions of different combinations. But the result would usually be only few of them are repeated again and again. So we would need to understand how 2 cortical patches interact with each other to measure these neurons, find out what are the repeating constellations of firing, and then try to understand what is their meaning. Now, this is very difficult. So the letters of communication and cortical activity are patterns in 260 neurons. But what are these letters and what do they mean? We do not know, and we have no chance of knowing it now, but there is a chance of knowing it in the future. It is easier for me to explain what would go on if we take neural networks for which we know what's going on. So in multi-layered perceptron, there are inputs that come to some 1 or more layers, and they converge on small number of perceptrons, at least 10, usually more, and some combinations of their firing have a meaning, and we need to resolve what are these combinations that come out as a result of computation in this patch, and what is their meaning. I want to give an example from the simulation of a network called NetTalk. So NetTalk was developed by Sejnowski and Rosenstein, and it looks like this. The intermediate layer looks at 7 characters. It tries to generate the vocal tract properties that generate the phoneme of the central one. So here, the I. So there are 120 units in the intermediate layer. There are 26 perceptron out there, because it turned out that every one of the 50 phonemes of the English language can be expressed by some combination of firing of these features that control the vocal tract, the voicing, non-voicing, and the airflow. So there are 26 perceptrons. 26 perceptrons had over 67 million combinations, but only 50 of them are the phonemes that make any sense. I'll try to let you hear how it works. So let me see how I can do this. Not friendly.
It might be on the other screen.
Or you sound like that.
Demonstration of Network Learning by Terry Sinofsky and Charles Rosenberg. Learning corpus taken from Carteret and Jones, informal speech, first rate transcription. The first recording represents the first 5 minutes of learning with the network starting from 0 waves. The second recording gives the performance of the network after 20 passes through a corpus of 500 words. The third recording shows how the network generalizes to fresh text. First recording, de novo learning.
So you got the idea. Just a second.
Second recording, after 10,000 training words.
When we walk home from school, I walk home with 2 friends, but sometimes we can't run home from school now. Because someone got every time she wants to run. She gets very muzzle stuff, and then she can't breathe on her rear end when she gets sick. That's why we can't run. I like to.
You got the idea.
After 10,000 training words.
Okay, you got the idea. So you can train a network like this to generate the combinations of activity in 26 perceptron that corresponds to 50 phonemes in English. So you need to understand which combinations represent a phoneme in order to say we understand what's going on here. You see the text and 16 perceptron change the vocal tract such that it generates one of the 50 legitimate phonemes. Okay. So nowadays, such networks have many intermediate layers. There's also feedback, and there's something called deep learning rather than backpropagation of error. And the principle is the same. All of the intermediate computation end at some perceptron. Only few of the many possible combinations of the perceptron activity are meaningful. So what's in the cortex? We said cortical connection is patchy. There are patches, and how many neurons in the patch we need to measure in order to understand what is the output of this patch. Let me take another example. Another example of a network is the attractor neural network. In the attractor neural network, there are groups of neurons that excite each other and inhibit everybody else, such that this group stays active and the rest is silent. If you start for something which is not exactly this group, it usually would converge to this group. I want to show you an example of that, a very simple one. So, yeah. פה אני רואה את זה, ופה אני לא רואה את זה.
אעביר לך את זה בכלל. כן, כן. היום... Sorry. So, from the beginning. And...
זה מוצלח, אני לא רואה את זה לא פה ולא פה עכשיו. אוקיי, רגע, נזיז את זה שוב להתחלה.
אוקיי,
כן, מספיק. אוקיי, מספיק. So, here is a single neuron, a single network. I embedded this X, O, and H configuration of firing in this network. So it's the same network. We may start with this initial condition. So we start with this, we let it evolve, and you see that it's, when it's active, it converges to this shape. However, if we start from this configuration, here we start and let it evolve, it will fall into this figure. And if we start with this configuration, it will fall into the H figure. So it's the same network. Depending on the initial condition, we get either one attractor, another one, or the third one. So here, because I put the order in these neurons, you know that this configuration means X, this O, and this H. But if I mix the neurons, but retain their connection, you'd get a strange shape here that you don't know what does it mean. Okay, thank you. So the latter groups of neurons that fire at high rate are the attractor, and the rest are silent. And there could be several attractors in one network, and each neuron can be member of several such groups. How can we tell if something like this happens in the cortex? לא רוצה. אז מה אני צריכה לעשות שזה יתקדם? Okay. Another model for activity is the SynFire chain. I want to show you how SynFire chain looks. So would you press please on this arrow? זה אצלך עכשיו. כן, יפה. Okay. So this is a simulation of some 200 neurons. There is a lot of noise. So sometimes I hope you don't get epilepsy. So sometimes the neuron fires and it turns black. Sometimes there is stimulus applied to the neurons here, but like now, you get activity in the network. here is the total level of activity for a while, and then it finishes. If instead of this anatomy quotes, we plot the synfire chain, so each of these 8 neurons connect to the next 8 neurons, which connect to the 8 neurons, and so on. It's a feed-forward network. Each layer have 8 neurons, and they connect to all the 8 neurons in the next layer. So if we give a stimulus, you can see it generate a wave that goes through the network. You can appreciate what goes on if we do it in slow motion. Stimulus in slow motion. Stimulus is applied, it's just depolarization. Few neurons fire. After a while, it gets organized into this synchronous wave that proceeds through the synfire chain. So this is what I mean by synfire chain. So could you please turn it off? Okay. Next slide. So I want to show you some computation by synfire chain. Would you please turn this on? Okay, here there are 4 brain regions. This region is sensitive to shape, this to color, this to taste, and this to some complex like tuna salad, egg salad, and so on. Now, right here, we started by stimulating this shape and the yellow color. And without stimulation, that turns away with the synfire chain of the cucumber taste. Synchronous waves in this shape, this color, and this states, they symbolize a banana. You don't need a special brain region for banana. It's this synchronous thing that banana. Okay, turn it off, please. And then the next one. Thank you. So now we are eating fruit salad. We have a piece which is yellow and this shape, and by itself, this turned out the taste. So you have the taste and the yellow piece, and by itself, this turns on the shape. So by taking a piece from the fruit salad of taste and yellow, we know that it is a piece of a banana. Okay, so synfire chains can associate initial conditions with a continuous thing. They can complement shapes, and they can associate shapes like other neural networks. They have the advantage that the place of the wave in the chain tells us something about time. Think about the situation where you see 3 letters, G, O, and D. Now, if all you have is a group of neurons that fires for the G, another one for the O, and another one for the D, you don't know if what it says is God or dog. But if it was synfire chains, the order of the synchronous wave will tell you whether the G was the first one or the D was the first one, and so on. So synfire chains have the advantage that they code also time of when something starts, and this is used by us to interpret things. Okay. So by just looking on the activity in the shape neural network and the color neural network, we don't really understand what goes on. If we know that there is a synfire chain here that calls for banana shape, and a synfire here that calls for banana color, and there is a synchronous wave in both of them, we do know what's going on. Now, unfortunately, we don't have anything like this for the cortex. So let's try to understand what we can do for the cortex. So if we stimulate simultaneously record neurons in a patch, we might try to understand what does the patch computing and what its output representing. And from all the combination of the 260 neurons that project from the patch, only few would return again and again. And those can be thought as letters of the brain alphabet. How many neurons do you have to record to recognize that something like this happens in a patch? So Gersten and colleagues tried this in a simulation of 40,000 neurons with many simple chains in it. And they found that if you record simultaneously from about 200 neurons, it's enough to say that there are patterns that repeat and develop one after the other, and which other parts. So that means that with recording 200 units in a patch could help us understand what's going. Recording of 200 units are available today. However, they are distributed over two larger space. We need 200 neurons within a patch, which is about 1 millimeter of cortex in men and about 0.5 millimeter in monkey, and about 0.1 millimeter in a mouse. So can we say something about what's going on? We can say how precise firing times are. Here is an example from the work of Shmuel, or a student of Menat Pater and me, that try to estimate the precision of timing in firing rate. So here's a cross correlation between two neurons recorded through two different electrodes. And you see that at this delay of 20-something milliseconds, there were 30 coincidences of firing of one neuron and then of the other. And this seems to be higher than the background. What is this represent really some timing accuracy? We can use the idea of Eli Bienenstock, which said, how could we know if timing accuracy in the brain is important? Suppose we have a drug that we can put in the brain, and this drug has the following effect. Whenever the membrane potential of a neuron crosses threshold, it will delay its firing within W milliseconds. So the firing time would be not locked exactly to the zero crossing, but jittered in some window, W. So we can take this activity of these two neurons, jitter them within a window, each spike within a window of, say, 10 milliseconds, do it 1,000 times and see for each jittering case how big is the highest bin in the cross correlation. It may be here, it may be here, it may be here, it may be there. This is the distribution of peaks in the cross correlation of the jitter data. And this is what we got in the experiment. Clearly, the probability of this, if accuracy is 10 milliseconds, is less than 1,000. So this was, I believe, this day, 14 September. For 10 millisecond jittering, it's below 1,000. Same for 9, 8, 7, 6, 5, 4, 3. But for 2 milliseconds, it gets out of the 0.5 or 0.1 chance of being, probability of being chance. So for this neuron, the accuracy is about 2 milliseconds. Shmuel did this for 8 days, and for 1 day, the accuracy is better than 0.5 millisecond. The timing accuracy of the spikes here was recorded with 0.1 millisecond accuracy. So in one of the pairs, the accuracy of timing is at least 0.5 millisecond. This is only one case, but it's very strange. It reminds me of a story about Ramachandran. Ramachandran was a neuropsychologist working in hospital, working on people with brain damage. And at one time he gave a lecture about a patient that had very localized brain damage, yet have very specific language deficits. At the end of the language, somebody raised a question. It's very interesting, he said, but this is only a case of one. So Ramachandran told him, look, had I brought in here a pig that speaks English, would you also tell me it's only a case of one? So for me, this thing is a pig that speaks English. Okay. So we can also argue that such accuracy suggests that activity is organized in synfire chain, but that does not prove it. For real proof, we need to record simultaneously many neurons from one patch, and this many is at least 200. We don't have this ability today, but we are not far from it. So my conclusions are, we have proof that there is structure beyond just firing rate. The structure is associated with precise firing time. We do not have any idea what are the letters of these cortical activities, and this is something which we seek to study. Recording of many neighboring units is required for finding such letters. Thank you. Questions and comments? Yeah.
This is interesting why you assume that the information spin is of a discrete nature. It's a set of bed. Whatever you want to spin a continuous bed, angle. Any continuous variable basically, just the same.
You can think that in each synfire chain, there could be several waves going one after the other. If you have one synfire chain for this direction and one synfire chain for this direction, you can think that if something is in between, you get less waves in both this chain. So the number of waves is the strength of the stimulus, and you can vectorial sum this number of waves here and number of waves here to know what is the intermediate thing. So you don't need to have separate chain for every possible angle. You can have by few chains in different direction and activation of some of two of them in different degree, know what is their intermediate thing. Yeah.
So one could take your conclusion to the question, why don't we understand how the brain works, is that, well, technology just isn't there enough, and when we have a technology by which we can measure 200 adjacent neurons, then we will know how the brain works, right? I don't think that's what you meant. And I think the other title of your talk, which was we have so many neuroscientists, also alludes to something in the way that, neuroscientists have been approaching this question. So,
thank you. You touched a very soft point. I don't really understand what is to understand how the brain works. Okay, so what I'm suggesting that the brain works by communication between patches. Each patch has few output combinations that represent its computation outputs. They interact with each other, and this altogether generates something that is what we see as brain mental process. And this is quite diffuse. And by measuring single neuron, we will never get to it. So my suggestion is that when we get the ability to record large number, like 100 or 200 neurons from a single patch, in a behaving person or animal, we would be able to see what are the letters that this patch generate. And if we have this for many patches, we'll know what the words, even more patches, we know what the sentences, and we can get the meaning out of it. That's my claim. Okay, yeah.
Thank you. So in the frontal cortex, and perhaps in other brain areas as well, we know that many neurons have mixed selectivity, which means that they respond to many kinds of different tasks.
Yeah.
So in the model or computation that you suggested, this is something, the computation is fixed, so it's predetermined. How do you think SynBio would work to account for such mixed selectivity properties?
There are two studies in the literature about something that's called SynBio chain capacity or something like this. And they try to estimate from connectivity and firing rates how many SynBio chain links you can put in a small patch of cortex. And the number of links is the same order of magnitude as the number of neurons, because it's a combinational thing. So this neuron combined with this is one thing, and it's combined with this is something else. So the number of SynBio links that you can put in a little piece of cortex, if the links are about 100 neurons wide, is about the same as the number of neurons. So now whatever you want to compute with single neurons, you can make a network that computes with coincident firing of few neurons. And the difference would be that each neuron fires only few spikes. You don't spend a lot of energy. And that if 1 or 2 or 3 or 10% of the neurons die out, like in my brain, it still can function. Yeah.
I was also wondering during the talk regarding the role of the endogenous activity and spontaneous activity in such a model, because this model relates the external stimulus to the brain activity. We know that the brain also computes other sources.
In my view, the brain always computes something, think of something, understand something, so on. So all the activity that when we study, we think it's noise. It's not noise. It's other computations which are not related to what we are studying. And I don't think spikes are wasted. I think even if you see a single spike, a spike of neuron that relates to some SynBio chain that happen to be active at this instant. תודה רבה על הסבלנות שלכם.
תודה רבה. אין לי מילים. נהפוך הוא, זה היה